Hello, I'm Suneeta. I work as a senior data scientist at Nearmap.
And I'm Martin Abeleda, an engineer working at Nearmap, and we're working on the stability of our inference pipeline.
Nearmap is the leading provider of high-definition aerial imagery. We specialize in providing current and crisp content, and we do so in various formats such as 2D, 3D, intelligently derived layer, and more. We frequently capture urban areas of Australia, New Zealand, United States, and Canada. To do so, we fly our plane at a height up to 18,000 feet, and that allows us to capture thousands of kilometer square area in a single flight at a very high resolution such as 5 centimeter per pixel. In just year 2019, we captured 2.5 million kilometer square area. If we were to print out our image and stack them up, in just 1 year, we would have created 4 Mount Everest equivalent content. And it's got to be this way because we are data as a service organization, and we truly are a big data company. Today, I'm going to be talking about what we do with AI at Nearmap, what are the expectations we have when we talk about offline inferences, and then we talk a bit more about our solution that we call SEER. Martin will pitch in and talk about some of the adventure we have had when running this solution at scale. And he would also talk about some of the annoyances that we have encountered with respect to cloud infrastructures. And I'll come back in to talk about some of the misadventures, and then we'll open the floor for questions. At Nearmap, our AI team has been focused on associating semantics to the pixel, and we do so to find information about location. What you're seeing here is Sydney's most livable place. This is Milson's Point and Lavender Bay from the eyes of our machine. This is roof, swimming pool, water body, and building outline overlaid on top of it. Of course, we do a lot more than these handful of attributes I'm talking about. What we do is we generate petabytes of derived content from terabytes of aerial imagery. But we already got petabytes of imagery. So you see we are exponentially growing our already big data set. The solution we are talking about today, we call SEER, can produce semantic content at a rate of 70,000 kilometers square a day. We could probably do a lot more, but we are limited by the availability of spot GPUs in the cloud. Now the data that we generate, or we have already generated, is already being put to good use in the industry. It's available for consumption under AI offline beta program, and it's already delivering solution in the space of 5G, insurance, energy utility, urban planning, and a lot more. But we don't just stop at associating semantics. We want to provide insights from micro level such as pixels all the way up to macro level such as world. And we are already doing that. Some of the examples are all on the screen. Now to do all that, we observe a workflow, end-to-end AI workflow, somewhat similar to what's shown on the screen. Now we own everything starting from the data collection and to model operations such as training, tuning, improvising, and also to inference, and at the end to insights as a service. Now as you can see, there's a lot going on here. And as Cully has pointed out in 2015 NIPS paper, that machine learning is, the ML code is really a small part of a big system that forms machine learning. For us, Kubernetes has been instrumental in realizing this end-to-end AI platform and also pushing boundary in terms of scale and the volume of data that we crunch. And for that, a big shout out to Kubernetes community for making this amazing tool. Now today, we are only going to be talking about offline inference, which is the section of this complex workflow shown on the screen in red highlight. When we talk about offline inference, the modus operandi really is for that operation is what we call DAG, which is a series of operations applied on an input data set. Our expectation with the DAG is that each step in the DAG process needs to massively parallelize. We basically beat the hell out of each of the steps. And the way we do that is we slice the input to the step into various atomic units that we call datum, and then the operation gets executed in a gang scheduling semantic with each task in the gang consuming one datum each, and it keeps happening until we have reached to the leaf node. That's when we obtain all the final data that we are interested in, store that back into object store, and clean up after ourselves. And as you can see, this is quite a stateful workflow, which is the essential component of our offline inference engine. Now we expect that this engine is able to cope up with the constant flow of capture throughput, but at the same time it's able to deal with the bursting load for cases when we have to run inferences over million kilometer square areas in very short time, such as a week. And to do that, we really need thousands of nodes, and not just CPU node. We primarily do deep learning, so we are talking about teraflops kind of operation. So we do heavily use GPU in our case, and that really leads us into using a mixed compute of GPU and CPU. Because we are doing all that at such a scale, we need to be efficient in terms of cost, turnaround time, and utilization of the resource that's available to us. And we need to be resilient with our workload because that helps with chaos, and it also helps a lot with the cost. And we don't need any manual bottleneck in our system because we can't be running at that scale if we have a manual bottleneck. So that's really a key component of our system. At the time of building this solution, we looked at off-the-shelf available solution. Now these are great tools, but they weren't quite production ready and weren't quite doing what we wanted. Argo, Pachyderm, and Kubeflow pipelines, which is a wrapper over Argo, they are great tools and we already are using them in some capacity. But particularly for offline inference, they weren't quite doing what we wanted. Most couldn't cope up with the load, and in some cases there were over or under provisioning, or execution model was too expensive. So what did we do? We built our own solution. That's SEER we are talking about. How we did that is we exploited Kubernetes extension endpoint that's known as custom resource definition, If you aren't familiar with CRDs, then you might have heard term operator, which works on a similar paradigm. There is only slight pragmatic difference between the two. So now I show you the architecture of SEER, which looks somewhat like this, and you might think there's a lot going on. Let me take you through in a step-by-step fashion. First up, the CRD and the controller. So what we have is a SEER job, which is a CRD, the declarative spec defined, that corresponds to the DAG that we have. It holds the step of operation that needs to be applied along with the input operation. Now, controller keeps watching for any new resource creation, and upon creation it acts. The way it acts is start of these components. First is the SEER workflow, which under the hood is a job. And aside from the job, it also creates some other resources such as persistence, volume claim, storage class, and a deployer. Now, these are the key component that allows for gang scheduling. What happens under the hood is we are creating a network file system that's cross AZ and open it up in a read-write many semantic. And this allows for a concurrent heavy read-write and thus realizing the stateful gang scheduling. And as a part of the SEER workflow job, the pod gets started. The soul, which again is a controller. So SEER workflow is a controller, and responsibility of this pod is to ensure that the DAG execution happens in the way we expect. Now this leads us to the DAG, which is the bit that's shown on the corner. Now this is a synonym of what our workflow would look like, and as you can see, some steps are independent and singleton, but other steps run at high parallelism in gang schedule semantic, as I said before. Now they consume their own respective datums and perform the operation. At the end of the operation, we collate the data, feed into the next step. We keep doing that until we have reached to the final stage. That's when we clean up after ourselves and remove all the resources. Now this solution, with an extension to Kubernetes, creates ephemeral cubes for us. Now we don't run them forever, we run them as on need basis. These are self-managed multi-AZ Kubernetes cluster provisioned with KOps. We primarily run on AWS, but we often see the cases when spot GPUs run out on AWS in their data centers because we are running at such a capacity. In those cases, we go out and run on GCP. So that means this solution is cloud agnostic. Like I said, this solution is multi-AZ. We run with 3 master, up to 3 on-demand nodes, and then we run a fleet of spot GPUs, hundreds of CPU compute and thousands of GPU nodes. And we don't just have one Kubernetes like that, we would have multiple Kubernetes depending on the capacity of the system. Now, to deal with the scale and the volume of data that we're talking about, we are running too many nodes and too many pods. We're talking about of the order of tens of thousands of pod and thousands of node. We need to be careful with the placement of our resources and utilizing the resources that's available to us in best of its capacity. To do that, we utilize placement predicates quite heavily, and some of these are selector predicates, anti-affinities and anti-affinities, taint and tolerances. In terms of quality of services, unfortunately, due to nature of our load, not many are guaranteed, but we do our best to ensure that they are burstable. Wherever not possible, we fall back to best effort. But together, all these components, with the help of autoscaler, allows for the scale that we are running at and helps us realize our goal. Now, Martin will be taking over to talk about some of the adventure we have seen in running this solution at scale.
Thank you, Suneeta. So no project is complete without its fair share of adventures. And running thousands of nodes and tens of thousands of jobs in the cluster has been quite a challenge. With this kind of load, we can't guarantee that there's enough resource in the spot market to run everything in parallel. And so we've got contention between resources with lots of pending pods, except not all of these pods are created equal. We really need our controller and our master pods to have priority when we allocate them. So here our solution is to create a priority class, and we assign this to those pods, ensuring that the critical processes have affinity for more stable on-demand nodes. And this allows us to schedule tens of thousands of jobs with separation between the critical orchestration jobs and then the data production jobs, which trickle through as load becomes available. So we can keep our resource fed without affecting the management processes. So we're in a pretty good place. We can create batches of jobs, but we need to be able to manage running multiple of these DAGs at a single time. The thing we're missing here is a queuing mechanism, and this allows us to operate processing of many jobs at a single time in an automated way. Again, here we've created a custom solution, and we've extended the controller with two components. The first one is a database backed by persistent storage, and this captures our queue and also the state of jobs in flight. And this is wrapped by a service which allows us to query the state of jobs and update. The second component is a scheduler, which monitors the state of jobs in the cluster and looks at the capacity of the cluster and decides whether or not we're able to schedule new jobs. And this allows us to trigger and queue our workflows for processing, and we can ensure that everything runs in the right order, that we don't overload the Kubernetes API, and that we're feeding our resources as efficiently as possible. So at this point, we're running multiple workflows simultaneously, each of them with thousands of jobs scheduled at a time. And we're running a stateful workload here, so we require a cross-AZ persistent store, and we're accessing files repeatedly. So with thousands of nodes, each doing a mix of read and write operations, we're starting to see ourselves hitting the limits of the shared file stores. So our solution here is to isolate the persistent volume for each of these workflows. And again, we provision across AZ and FS, but share this only between the jobs in that workflow. And this provides a good isolation between each of those, and then we can throw this away once our processing is finished. So it allows us really to keep our processing times in check by keeping our GPUs fed and running high concurrency. So introducing these PVs has also added some stability issues, and we see particular nodes failing to mount the volume, and this manifests itself in pods which are stuck in a container creating state. And so at the moment, it's still an open issue that we're seeing in the community, but for now to hit full automation, we've gone with a custom solution, and what we've done is we've deployed an agent onto the cluster. And this resolves this issue when we see it by draining the unhealthy nodes. And again, remembering that we're running a self-managed Kubernetes cluster with burstable or best effort jobs, we see occasionally that we steal node resources from system components like the kubelet. And again, this is an issue that many people in the community have seen. But for this one, there's a well-documented best practice solution. And so what we've done is we've manually reserved the resources for the kubelet in the cluster spec. And although it's not necessarily a difficult solution, we think that it should really be pre-configured since Kubernetes should be, is intended to run at this scale out of the box. So now we're at a point where each of our pods can run without harming system components or running out of I/O or hitting I/O limits. And given that we're scheduling in the order of tens of thousands of these at a time, we need thousands of nodes to process these in parallel. And so with a default container network interface, we're limited to a route table limit of 50 entries. And we see degradation if we cross this. And we could either raise this limit with AWS at the expense of a slight performance degradation, but that only helps us in scaling to hundreds of nodes, which isn't quite our cup of tea. So we've looked at the option of changing the CNI to Flannel for its simplicity, and that allows us to go up to thousands of nodes in parallel. And at this point, we're running a healthy cluster with a configuration that allows us to orchestrate tens of thousands of pods, but it's not completely pain-free, and we start to see some issues with the cluster auto-scaler when going beyond 650 nodes. In this case, the cluster continues to look healthy, but the auto-scaler can't reach our masters, and we suspect that this is due to a timeout issue. Again, this is an open issue which we don't have a resolution to at the moment, but we have a bandit-like solution here, good old bash, and when we observe auto-scaler failures, we fall back to a pre-cooked script, which acts as our auto-scaler. And as a secondary measure, this does the job. So now we're running at the scale we want, but we need to finish as fast as possible. And in our workflow, the GPU step is by far the most expensive operation, both in terms of cost, but also in compute time. And we typically see processing times of up to 3 hours for each of these datums. So really, to process this in any acceptable time frame, we need to parallelize this as much as possible, using as many GPUs as possible. But who would have thought that there wouldn't be enough spot GPU in the cloud? So going multi-AZ wasn't enough, and we've embraced a multi-region approach. And what we've done is we've provisioned a cluster in every AWS region that has enough spot GPU availability. To achieve this, we've adopted a GitOps workflow, and we orchestrate the clusters with kops and Terraform. And every code change triggers a CI workflow, which propagates through to our clusters. And this gives us all the benefits of version control, but also folds into our existing code review practices. So we've gone out to multiple regions, and we have a mushroom effect with our clusters. Our queuing and scheduling mechanisms have been decentralized, and this requires a bit more work to operate, considering that we want to really be in a fully automated manner. So we want to centralize our queuing and scheduling mechanisms, and we've done this with Istio. So each of our clusters has its own service mesh, which together form one logical hybrid mesh. And with multi-cluster Istio, each control plane runs its own DNS server, which allows discovering services from other clusters. And this really is the final step to having a fully automated distributed cluster, and is moving into production soon. So now we're in a place where we're running thousands of nodes, generating terabytes of data per job. And the next challenge is pulling this data into our object stores so that we can serve it. It's not quite as simple as running a single S3 sync, as others have found, and we observe missing files, especially when we're working with terabytes of data. We also tend to see interesting things like this. We get corruptions when GPUs crash, and as you can tell, these aren't roofs, even though that's what they're supposed to be. So we've added a final verification step, which is a comprehensive verification, and is our final guarantee that everything is there and valid. We've also managed to hit quite a few bottlenecks within the infrastructure, because it turns out that cloud providers aren't used to seeing people hitting this scale. The first one of these is hitting node provisioning limits, because we want to be able to scale up to thousands of nodes in just a matter of minutes. But by default, AWS provisions nodes in blocks of 10, which takes about 40 minutes to hit that scale. And it turns out that's not all. We're hitting infrastructure limits everywhere you can imagine. And it's a process of jumping through each of these limits until we can hit the scale that we desire. So now I'm going to hand back to Suneeta, who's going to talk about some of our misadventures as well.
Thank you, Martin. No adventure is ever possible without a few handful of misadventures, and that's what makes our experience interesting. So let's look at some of these. Sharing GPU. What do we do when our GPU workload isn't quite GPU efficient? We share the GPU, right? So we thought. And when we ventured out to this exercise, first attempt at this, we exposed all the GPUs of a node to all the pods deployed on the node and only share a fraction of the memory through TensorFlow configuration. Turns out that even TensorFlow doesn't guarantee the amount of fraction that you are intending to allocate with that fraction configuration. And that's not it. There are various spurious errors that you would see with your stack crashing and GPU compute crashing. Some of them are so nasty that they would fail they would not outright fail, they would fail silently, and you would have absolutely no idea of crash. And what that leads to is perfectly readable output, but complete garbage. One such example is shown on the screen. Now, when we run with this particular attempt, we generate thousands of these. These are of no use to us. And of course, that's not quite right what we are trying to do, because there is no isolation guarantee on GPU. The GPU providers such as NVIDIA, for security and isolation purposes, they don't recommend this approach. But one attempt and one exercise wasn't enough. We still were hell-bent on it. We tried one more exercise. We looked at exposing GPU memory as an extended resource, similar to what Alibaba Cloud exposes in another semantic. It works for a lot of people, but it didn't quite work for us because, again, like previous discussion, we would have spurious OOM errors and a complete rubbish files getting generated all over the place. Turns out all we needed to do was optimize our code so it's efficient on GPU, and it wasn't as much effort as it did for us to run through 1 and 2. Now, GPUs are expensive, right? And as we said, we run thousands of them. So when we run with Spot, we can get them at about 40% price, so we thought. And then when we bid for them, we bid for max on-demand price, and then we get for whatever is the relevant price. That sounds perfectly reasonable, right? Just when you start running thousands of those and drain the cloud or the region with Spot GPUs, then the market starts to go up. You know how spot markets work, right? As the demand goes up, the price also starts going up. But when your system is automated and you are bidding for the max price and happily sipping your drinks, then things like these happen. The price spiked from 6% all the way to 120%. And yes, we ended up realizing that when we got our bill. And yes, I still have my job. Thank you for your concern. So the solution for this was quite simple. All we had to do was bid for the price that we are comfortable with. Now, monitoring GPU isn't as simple as monitoring CPU and memory when you lend out VMs from cloud infrastructure, because that's something that they own, and it's easy to isolate from the virtualization point of view. Not quite so for GPU, because you still need to install the drivers and toolkits to be able to probe the GPUs. But we needed to explore that because we wanted to improve our code so it's 100% efficient from GPU viewpoint. So what we did, what a common solution would be, we deployed a daemon set that frequently polls into the GPU to find the utilization. But turns out we're now running so many daemon sets that scheduler can't cope up with. We already have thousands of pod. Now we have Flannel for networking component. We have monitoring daemon sets. We have device plugin, and we also have GPU utilization. And system is starting to freak out. We could probably do better with these daemon sets. So what we did was we co-located these with the device plugin, and that seemed to work for us. But of course, now NVIDIA has a GPU operator, so that takes away the pain of deploying the daemon sets. So thank you, NVIDIA, there. Now, we would like to thank you all for coming to this talk, and we hope that our experience was interesting to you and you find you have learned something from our experience. Now, I would like to take questions, but before I open the floor for that, I would like to let you know that we are hiring for AI team, and we have 2 open positions. One is data engineer, and the other one is machine learning engineer. Martin and myself would be hanging around for the rest of the day, so please come and find us. We also have Mike with us from our team. He is sitting somewhere. Please wave out, Mike. So he's out back there. You can find him as well. Now, back to being nice and opening floor for questions. Thank you. We have one on that side.
Okay.
Hey,
Hi.
I have a question on the GPU sharing. You mentioned you got a solution from Alibaba on GPU isolation and scheduling. Did you try that? Is it working, or why it's not working for you, and why it's working for some people?
Yeah, sure. So I could talk about that. So the way the Alibaba Cloud's GPU extender works is pretty much you know the total memory of your GPU, and then you extend the Kubernetes scheduler to expose the GPU memory as a resource. You know how you expose memory or CPU, and you sort of say that I only want one CPU for this pod and only give me that. In the similar semantic, you would say that I only want, say, 400 MB or 1/3 of a memory from the GPU, and semantics like this, and you would expose like that under a certain key, and you deploy your pods. But fundamentally, the GPU, like NVIDIA, itself doesn't guarantee isolation on your GPU. So you can take one GPU and slice the memory and use your workload, but it's not guaranteed that you will not step over and consume any more memory if your workload start to spike up and use more memory. And similar to the attempt that we had one, the same problem exists in attempt 2. There is no isolation guarantee. So even if you are asking for half of memory, you are not quite guaranteed to get it. And that's the problem that we had running in attempt 2, because like I said before, isolation isn't quite guaranteed from the GPU providers itself. There are security and isolation concerns to start with. And if you read up their design document, Alibaba Clouds, they are very clear in saying that it's not guaranteed. It works for some cases, like if you are running very small load with GPU and you kind of guarantee the same throughput with your workload, then it would work. But we run quite heavy image processing and deep learning workload, and we do spike on GPU a lot, and that's why it doesn't quite work well for us. I hope that answers your question.
Thanks for the great talk. It's really interesting stuff. You did mention Kubeflow, Argo, Pachyderm. I'd be interested in what your thoughts are on something like Kubeflow serving and how they're going about auto-scaling inferencing.
Great question. So I have to start with the notion that by the time when we started thinking about KF serving and Kubeflow serving was still evolving, we already had this solution running and producing at scale. We are talking about running over 1 million kilometers square back in February, March timeframe. So that time we already had solution running at scale and doing the things that we are talking about. And at that time, these tools were not evolved yet. Like, Kubeflow is not quite production ready yet. We are talking about January for that to be production ready. And like looking at the scale of things we are doing, you would want it to be production ready and really have passed the stress test. That wasn't quite done for us, and these are great tools. Like I am all for Kubeflow. KF serving sounds really great, and the fundamental idea of Kubeflow taking away bringing in the abstraction over workload is great, and we are all behind it. But it just didn't do the things when we wanted for us. So we are definitely evaluating it. I'm not ruling that out as such, but this is what we did when solutions weren't available.
Cool.
Thank you, everyone.
Thank you very much.